I chose to review the Beckmann Rearrangement. And the Beckmann Rearrangement is a conversion from an oxime to an amide, typically using an acid catalyst. In this case, the example is sulfuric acid. So here's the mechanism. We have an oxygen attacking a hydrogen from a hydronium ion, resulting in a neutral water and a positively charged oxygen here, which is here. And then the positively charged oxygen leaves as a water because it takes the electrons from the nitrogen here. And that results in the electrons from the carbon here moving over to the positively charged nitrogen because it needs them more than the carbon does. So in this specific example, that will move our ethyl group over to the nitrogen, leaving us with a positively charged carbon. So that positively charged carbon will be attacked by the oxygen of a water molecule, which will leave us with a positively charged oxygen with two hydrogens attached. It doesn't really matter which of these sides it gets attached to. This will either create an E or Z isomer, but at the end of the tautomerization step, it won't matter which it was. Because that double bond will no longer be in the central separating them, but it will move out here. So it can just flip at that point. It doesn't matter which one was which. So at this point, we have a oxygen attacking the hydrogen of that positively charged oxygen, resulting in those electrons moving to the oxygen to stabilize it as an alcohol group there. And then it's at this point where tautomerization happens. And tautomerization will be the double bond here, connecting the carbon and the nitrogen, attacking a hydrogen here of a hydronium ion, resulting in a water molecule leaving and an extra hydrogen on that nitrogen. Because that carbon will now have a positive charge, the electrons from this oxygen move over, forming a double bond here and making this oxygen positively charged. Because this oxygen is now positively charged, the oxygen of a water molecule here will attack the hydrogen of the positively charged oxygen, and the oxygen will then receive the electrons from that leaving hydrogen, and that will neutralize its charge and give us our end result here. This is the reaction coordinate diagram. I think it'll be more efficient for you to read it than for me to try to explain through it because it's all labeled. But I will upload the slides so that you can review them in a more efficient manner in case there's any particular slide you want to get a better look at. This is the example of a use in recent literature, and it's visible light-induced Beckmann rearrangement by organic photoredox catalysis by Tang and the rest. And so Tang and the rest created a novel photocatalyzed Beckmann rearrangement that resulted in an excellent yield using visible light, organic photocatalysts, mild conditions, and more specifically, they converted ketoximes into their equivalent amides. I believe they were doing this to create a more efficient mechanism. So, to increase the reaction rate, polar solvents increase the rate of the Beckmann rearrangement because the rate-determining step requires separation of a charged molecule. That water leave the group at one point. So adding additional oxime reactant or removing amide product should increase reaction rate, right? That's kind of obvious, always removing product and adding a reactant. And then in this case, since it's exothermic, reducing the temperature would increase the reaction rate unless it just gets way too cold. So in terms of spectroscopic data, it loses a nitrogen-oxygen bond when it is converted from an oxime into an amide. So that nitrogen-oxygen bond should be visible at about 945 when it is an oxime, and then that should disappear when it becomes an amide. And there are my citations. Like I said, I will upload the slideshow so you can more efficiently review any slides that you may not have gotten a good look at.